Now we're going to delve into the mathematics of the Young's double slit experiment. So one of the things that we sort of need to realize is that the distance over here between the slits, let's just call this distance d, and this distance is actually very small. It's very small. Okay, we've just exaggerated here for effect. And the other thing that we know is that the intensity is obviously very bright over here. And what that means is that if this distance is really small, and if we have constructive interference that happens over here, and that happens over here, and if distance is very small, it effectively means that these two waves almost overlap each other, and that's why we have constructive interference over there. Now, what happens if we have, what about the constructive interference that is a little bit further away? Let me just do that with another diagram. So again, we're going to call this distance d, right? And that's just the distance between the gratings, between the slits. And then we have our most intense light over here. And we're going to just call that 0 because we'll see why we call it 0 in a second. But we're just going to call that 0. And let's call, because 0 stands for the brightest interference, the brightest constructive interference. And 1 will be the first constructive interference that is away from it. So obviously we have another one over here, and that will also be 1 because it's just one step away. And what happens over here is that this constructive interference, I'll just use green for this, goes like that, and then we have another constructive interference over here, goes like that. And what happens is that if we sort of draw an angle, right, that connects these two over here, so let's just call this angle theta, right? And if what I do over here, oh, actually, let me just use a different color. Let me use red. So if what I do over here is sort of draw a right angle triangle, okay, this right here is actually one wavelength. And it's one wavelength because it's sort of one step away from the first constructive interference. So what I'm trying to say is that, let's just say we have two waves, 1 and then 2, right? And so if we add these together, we get the brightest constructive interference, right? In order to get the next brightest constructive interference, we need to take the first one and move it. So let me just copy this, and let's do copy. Oops, actually, let me just clone it. Clone it. And so first of all, it was like this. This is the first constructive experience. And then we need to move it by one wavelength. So we need to move this by one wavelength. We need to move this by one wavelength to again get that constructive interference, so that it ends up, constructively instead of destructively. And so that's the reason for the 0 and the 1. In other words, we're sort of moving it one wavelength away. Now, if we do some fancy geometry, what we can observe is that this angle theta over here is actually this angle right here. And this is actually a right angle triangle. Okay? So let me sort of copy this into a new, so I'll just copy this part, copy, move to a new page, edit, paste, right? So let me just zoom in on this part, which is basically what I'm saying is that this is D, right? This is a right angle triangle, and this is theta. You can investigate why that is theta. It's just really simple geometry, but that's theta. And this is a right angle triangle. And what we said was that if it's the first wavelength away, it's 1 lambda. So what we can observe is that for the first one, it will be d, or actually, hold on, sine theta is equal to the opposite over the hypotenuse. So in other words, it's 1 lambda over d. Or we can rewrite this as d sine theta is equal to 1 lambda. Now what about the ones that are sort of 2 away, what about them? So what that means is we need to shift the curve, we need to shift the waves by two wavelengths, right? So it'll end up being the same thing, but instead what will happen is that the new diagram will look like this. This will still be d, right? We'll have a new angle, theta. Let's just keep calling it theta. But instead, this will be 2 lambda, right? And this will still be a right angle triangle. And what we'll end up with is d sine theta is equal to 2 lambda, right? And the same thing goes if we want the next level of constructiveness, so say the third one. So the third one will be, I guess you can't see it because, the third one will be here or something. I'm just going to take it off. The third one will be here, or, it's off the page on the top. But it'll follow the same pattern. It will become d sine theta is equal to 3 lambda, right? And so on and so forth. So if we let m be sort of the distance, or like the number of wavelengths, m represent the number of wavelengths for constructive interference. Oops, spelled that wrong. Constructive interference, then the equation just becomes d sine theta is equal to m lambda. And that's our equation for the Young's double slit. So remember, d stands for the distance between the two gratings. That's d over there. Sine theta is the angle between the first and the second. So from 0 to 1 or 0 to 2. That's the theta that we're interested in. M stands for the number of shifts that we have to do for the wavelengths in order to get constructive interference. And that's the equation that we're concerned with.